In this video, we'll turn our attention from discrete things like sequences and series and permutations and combinations, where our inputs were natural numbers, to continuous things, where our inputs are real numbers. We'll review some of the basics about functions that you've learned previously and introduce you to some new ideas. We'll start, as we always do, with the definition. A function f is a mapping from a set x to a set y in such a way that each x in the first set is paired with exactly one y in the second set. We typically call the first set x the domain of f and the second set the range of f. Since a lot of this is primarily review, we'll get right to the big idea. By learning just about everything you can about some basic functions, you'll be able to work with just about any function you come across this year in pre-calculus and next year in calculus. This year we'll be paying particular attention to the exponential function and the logarithmic function you see down here in the corner. Let's start off by recapping some simple graphing of transformations. Suppose we want to graph f of x equals 2 to the negative x minus 3. I'll start by graphing f of x equals 2 to the x, the parent graph, right here. The parent graph has a domain of all real numbers. And it has a range of all positive numbers. It also has two other interesting features that we should keep track of. One, it goes through the point 0, 1. That's its y-intercept. And then second, it has a horizontal asymptote along the x-axis. It tapers but never touches as x moves toward negative infinity. When we're graphing this function, 2 to the negative x minus 3, we can start by shifting down 3 units and drawing a new horizontal asymptote, recognizing that this function will still intersect the y-axis just 1 above that horizontal asymptote. And then lastly, recognizing that we have a minus x here on the inside of the function, and that negative 1 is going to create a mirror. It's going to mirror 2 to the x across the y-axis. So our resulting function will look like this. On the right here, we'll sketch a graph of negative log base 2 of x plus 5. Let's start with a graph of log base 2 of x. Log base 2 of x also has some very interesting features that are similar to what we've seen in 2 to the x. It looks just like this. This is log base 2 of x. This time, we have an x-intercept at 1, 0. And instead of a horizontal asymptote along the x-axis, we actually have a vertical asymptote along the y. It tapers but never touches. And so our graph of log base 2 of x plus 5 will look a lot like this. One thing you'll see, though, in the graph of negative log base 2 of x plus 5 is it's going to be shifted. It won't be shifted up or down because we have a horizontal shift happening on the inside of the function. This is going to be shifted to the left 5 units. And that will be the location of our new asymptote. And you also see an effect of a minus sign, but the minus sign in this case is outside the function. So that means it's going to mirror the graph. Instead of mirroring it over the y-axis, it will mirror it over the x-axis. So instead of swooping up like I did before, drawing my log graph like this, I'll swoop down and it'll look something like this. This will be the graph of g of x right here. You'll see as we go through this unit that graphing transformations of functions is just the tip of the iceberg of things that we can do when we understand our basic parent graph. One way to broadly apply your knowledge of the parent graphs is through the composition of functions. A composition of functions is when the result of one function is applied as the input of another function. So here's the idea. Suppose we have two functions, f of x and g of x. We can compose these functions in two ways. One, we can do f circle g of x, which is to say we're going to take the function f and plug g of x into it. Another way is g circle f. And this is when we take the function f and plug it in to g. Perhaps it's surprising that these don't result in the exact same function necessarily. Suppose, for example, that our function f of x was 1 over x, and our function g of x were 2x minus 1. When I do f circle g, then that means I'm going to plug 2x minus 1 into the function f. Well, f is the function that takes the input and puts it into the denominator. So this is the function 1 over 2x minus 1 that results when g of x is plugged into f. Meanwhile, g circle f is the function that results when you plug f into g. G is a function that multiplies inputs by 2 and subtracts 1. And so if my input is 1 over x, then g circle f will be 2 times 1 over x minus 1, which is 2 over x minus 1. Two very different results. In this example, we'll get a sense of how composition of functions allows us to create a new function from these old functions. Suppose we start with the function f equal to x squared minus 3x plus 2. That's a pretty simple quadratic function that we wouldn't have too much trouble graphing. We'll graph it here. And then we'll also look at the function g, which is just a simple absolute value function. We'll think about how when they're composed and we work out g circle f, or g of f of x, we create an entirely new function that has some of the properties of f and some of the properties of g. Let's start by graphing f. In order to graph f of x, I'm going to factor it. When I factor f of x, I get x minus 2 and x minus 1. This helps me find the x-intercepts, 1 and 2. I can also see from standard form that the y-intercept is at 2. That allows me to create a quick graph of f of x. If I wanted my graph to be a little more accurate, I could find its vertex. There it is. Meanwhile, g of x is very simple to graph. This is just the parent graph of absolute value of x. At this point, I'd like you to pause the video and think about what g circle f is going to look like. G circle f, of course, is the absolute value of x squared minus 3x plus 2. The key to answering this question is understanding how this absolute value function works and why it looks like a v. You see, the absolute value function, g of x, does one of two things to an input. It either leaves the input alone if the input is greater than or equal to 0, or it changes the sign of the input if the input is less than 0. This time, our input is the function f of x. And we can see that f of x as a function, sometimes it is greater than or equal to 0. And other times, it's less than 0. So the resulting function, when I compose g of f of x, will look exactly like this. In situations where f of x was greater than or equal to 0, g of x, the absolute value function, won't do anything to it. It'll leave it alone. Meanwhile, in situations where f of x was less than or equal to 0, absolute value will change its sign. And this is the result of the composition. When graphing composition of functions or trying to figure out domains and ranges, it's almost always best to use some technology to help you produce the graph, but to not blindly use the technology. Also use your brain and think about how those independent functions, f and g, are taking their properties and imposing them on the new composition. One important property of functions that we'll use frequently in this course is evenness. A function f is called even if f of negative x is equal to f of x for every x in its domain. An even function looks a lot like this zebra. It has a line of symmetry right here at the y-axis. And if you have a point on the graph with, say, coordinates a, comma, b, then that means you should also have a point on the graph with coordinates minus a, comma, b, because that fits our definition of an even function, where f of negative x is equal to f of x for every x in the domain. What that means is if you plug in the opposite signed x, you'd get the same y, the same f, as if you plug in regular old x. Let's take a long look at those parent graphs. Which of these graphs have the even property, where f of negative x is equal to f of x for every x in the domain? Pause the video and see if you can find them. There were 3 of them in all. The constant function is even. The absolute value function is even. And of course, the x squared, or the quadratic function, is even. If you have a point on the quadratic, maybe 2, 4, then you're certainly going to have the point negative 2, 4. In fact, every function with an even exponent is going to be an even function. That's how it gets its name. That brings up the obvious question is, can a function be odd? Of course, a function is odd if f of a negative x is equal to negative f of x for every x in the domain. So if I plug in a negative value for x, I get a negative value for y. An odd function looks a lot like this playing card right here. In fact, playing cards have odd symmetry so that no matter how you pass them out, they're looking face up. If you imagine fixing an odd function at the origin and then rotating it 180 degrees, you're going to get the exact same picture. That's how odd symmetry works. Perhaps a better way, though, to think about odd symmetry is imagining a point on the graph, maybe this spot right here. And instead of rotating the point, imagine mirroring the point through the origin. So when I mirror it through the origin, picture that point coming out the other side right here. Because we say a function's odd if f of negative x is equal to negative f of x. That is to say, if I have the point a comma b on the function, I'm also going to have the point negative a, negative b. If I plug in a negative version of the input, what comes back is the negative version of the same output that I would have gotten. Let's take another look at those parent graphs. We found 3 of these that were even. Can you find any odd functions in your parent graphs? Pause the video and see if you can find some. While there were 3 even functions hiding here, there were actually 4 odd functions. The linear function y equals x is odd. The cubic function, y equals x cubed, is odd. The reciprocal function, 1 over x, is odd. And the cube root function, y equals cube root of x, is also odd. One point to notice, though, is if you have that rotational symmetry through a point that's not the origin, then it doesn't classify as an odd function. So if you were to add 7, say, to y equals x and create y equals x plus 7, that's no longer an odd function. You might notice here, then, that we had 3 evens and 3 odds. And that actually leaves 3 other functions. These other functions, since they're not even and they're not odd, we just say that those are neither functions. That is to say, they don't have any special type of symmetry that we want to generalize. Let's take a look at an example. In this example, we're asked to determine whether the given functions are even, odd, or neither. One way we could do this is graphically, but since we don't have a grapher ready, we'll use algebra instead. To determine whether a function is even, odd, or neither algebraically, we simply plug negative x into the function and see what happens. When I do this to f, my numerator here changes from e to the x to e to the negative x. Plus, instead of e to the negative x, I'll get e to the negative x, which will be e to the positive x. And in the denominator, of course, I'll have negative x squared instead of x squared. And when I work that out and simplify a little bit, I notice that the numerator, since addition is commutative, I could rewrite it back as e to the x plus e to the negative x. And the denominator, since a negative x squared is really a minus 1 squared times an x squared, and a minus 1 squared is positive, I can just write that back as x squared. And so, in the end, I see that f of negative x worked out to be exactly the same as f of x, which tells me that this function is even and will be symmetric across the y-axis. When I try the same thing for g of x, something different happens. I plug in negative x, and I get 4 times negative x cubed minus 5 times negative x. This time, when I simplify, I'll get 4 times negative x cubed, which is negative 4x cubed, and then negative 5 times negative x, which is plus 5x. This is not the same as the g of x that I started with. However, I notice that I can factor out a minus sign. I can factor out a negative, and what's left inside the parentheses then is exactly the same as the g of x that I started with. And thus I can claim that g of negative x is equal to negative g of x, which tells me that this function g is odd. And therefore it's symmetric through the origin, or has a 180-degree rotational symmetry about the origin. Another useful property of functions is when functions are bijective or one-to-one, or sometimes they're called invertible functions. A function's one-to-one if no 2 elements in the domain share the same element in the range. One way you may have discussed this idea in the past would be with a test. We know that in order for something to classify as a function, it needs to pass the vertical line test. The vertical line test requires that if you pass a vertical line through the function at any spot, it can only cross the function in one place. Right? If that rule is broken, then we don't have a function. Meanwhile, we could also use a horizontal line test, in which we pass a horizontal line through the function at any spot we want. And if it only crosses the function in one spot, then that means it's impossible for 2 elements in the domain to share the same element in the range. And that would tell us that not only do we have a function, but we have a one-to-one function. That is to say, we have a function that is invertible, and we can find its inverse. All of our parent graphs are functions, so they all pass the vertical line test. But which are one-to-one functions? Pause the video and see if you can figure out which ones pass the horizontal line test as well. It might actually be easier to point out which ones don't pass the horizontal line test. The constant function doesn't, because it is a horizontal line. The absolute value function doesn't, and the quadratic function doesn't. But all the rest pass the horizontal line test. That means all of the others are indeed invertible. In fact, I can circle some here that are actually inverses of each other. The cubic function can be undone with the cube root function. Those functions are inverses of each other. Also, the two that we'll pay most attention to in this unit, the exponential function and the log function, are inverses of each other. The reciprocal function is interesting because it is actually its own inverse. What that means is, if you say find the reciprocal of a number, like 2/3, you'll get 3/2. And then if you find the reciprocal of 3/2, you're back where you started with 2/3. We'll see that sometimes finding an inverse can be a little more work than that. Given a one-to-one function, f, the inverse is denoted f inverse. Be careful with this notation because it certainly looks like f to the -1 power. But that's not how you want to read it. When you look at this notation here, you just want to read it as f inverse. And it's the function that maps the element from the range back to the domain. One way we can determine if two functions are inverses is through composition. If we compose the functions f and g in either order, f of g or g of f, you'll get just the identity x when those functions are inverses of each other. In this example, we're asked to demonstrate that these two complicated-looking functions are actually inverses of each other. I'll do this using the composition G, circle f, which is to say, I'm going to plug the function f into the function g. So that's going to look like this. I'll have g of 4 to the 2x minus 8. And g is this function that's going to take half of the log base 4 of the input and then add 4. My input is f. So I need to simplify this thing and show that it's equal to just x in order to prove that these are in fact inverses. This isn't nearly as much trouble as it looks, because I'll notice that I have log base 4 of 4 to a power. And since logs and exponentials are inverses of each other, those cancel out. And I'm left with 1/2 of that exponent, 2x minus 8, plus 4. And half of 2x minus 8 is x minus 4, and x minus 4 plus 4 is just x. In this example, we're given a function f of x equal to 5x over x minus 2, and we're asked to find f of 3 and f inverse of 3. Pause the video and see if you can work these out. There are a couple different ways you could have worked this out. One way might have been to find f's inverse. Let's go through that first. Let's say I replace f of x with y out of convenience. If I'd like to know the inverse, then all I need to do is switch the x's and y's, because that's what an inverse does. it sends the elements from the range back to the domain. So that means the inverse would look like x equals 5y over y minus 2. Okay, I can't stop here. I should solve for this y, because the y in this equation here is the inverse that I'm after, and it's nice to write y as a function of x and not vice versa. So to solve, I'll do this. I'll multiply both sides by y minus 2 to give me this expression. And then next, I'll distribute the x. So I have xy minus 2x equals 5y. And then I'll do some regrouping so that I have xy minus 5y equals 2x. Let me pause right here and just tell you my strategy involves getting all of the instances of y on the same side of the equation. The reason I want to write all of the instances of y on the same side of the equation is because that allows me to factor out the y. And factoring out the y is the first step in isolating it. When I factor out the y, I get y times x minus 5 equals 2x. And then when I divide both sides by x minus 5, I get y equals 2x over x minus 5. And this is the inverse that I was after. I'll use that notation, f inverse, and it's 2x over x minus 5. Let me write that back over here. I just want to point out why this is an excellent candidate for the inverse. One thing that an inverse does that we mentioned already is it switches the domain and range. When I look at my original function, f of x, I can quickly see that the domain does not allow x to equal 2. Because if I plug 2 in, I'll get a divide by 0 error. I can also see, when I look at f of x, that the range y could not be equal to, or I should say f, cannot be equal to 5. And that's because the ratio of the highest term in the numerator and the highest term in the denominator is 5 to 1. But this function will never be exactly 5 to 1 because of the minus 2 in the denominator there. And you'll note that when you look at f inverse through the same lens, the domain is x cannot be equal to 5, because when we plug 5 in, we'll get a divide by 0 error in the denominator, and the range is y cannot be equal to 2. The ratio of the leading term in the numerator to the leading term in the denominator is 2 to 1. So we can never quite get the y value to be 2. That minus 5 is always in the way down there. And we see that these are perfect candidates for inverses of each other because their domains and ranges have been completely switched. But what that means is I could have solved this problem much, much simpler. I didn't actually need to find f inverse in order to know f inverse of 3. Let me show you what I mean. To work out letter A, all I need to do is plug 3 in for x. 5 times 3 over 3 minus 2, that's 15 over 1, that's just 15. And then for letter B, all I needed to do was plug 3 in for y in the original equation. And that's because an inverse is just the original function with the x's and the y's switched. Inputs and outputs just turn around. I could solve this quite simply by multiplying both sides by x minus 2. To get this, I get 3x minus 6 is equal to 5x, minus 6 is equal to 2x, and thus x is equal to negative 3. And negative 3 is exactly what I would have got if I plugged in 3 here. That concept will be very important to keep in mind as we move throughout the year, that when we're looking at a function and its inverse, it's literally just inputs and outputs switched around. Let's wrap this video up with a little question in closing. Let's say we take two functions, f equal to the reciprocal function and g of x equal to 1 minus x. Of course, you can compose these in two different ways. You can do f circle g and you can do g circle f. These will produce two new functions. If you take those new functions and compare them with the originals and with themselves and with each other in every which way that you possibly can, and then continue to compose the new functions that you get with your old functions, how many distinct functions can be created? Does it go on infinitely? Or is there an end to all the madness? Think about it. We'll answer it later this week.